So it's really a big pleasure to have Daniel Gottesman this week. So Daniel, did really pioneering works in quantum computing, quantum information. Anybody that uses stabilizer codes and fault tolerance and GKP states, or many things that you use daily in your quantum information work were actually invented by Daniel. Yeah, so I also now heard that he's moving from Waterloo to Maryland, and today he's going to tell us about maximally sensitive sets of states. Thanks, Daniel.
Okay, thanks. So yeah, so I as Nate said, I'm currently at Perimeter Institute, and I also work with a startup company called Quantum Benchmark. And the work that I'm going to be talking about today is related to them, but I am moving to the University of Maryland this summer. So anyway, this work is really about, oops, there we go. Really about the problem of identifying errors in a quantum computer, and in particular, identifying a type of error called coherent errors. So let me first talk a little bit about intuitively what coherent errors mean, and then we'll come back later to define more rigorously what I mean by coherent error, and understand why I'm interested in coherent errors. So I want to make a distinction then between stochastic errors and coherent errors. So stochastic errors are kind of what you think of as terms of classical probability, that with some probability, say you might have an error on one qubit, and then you might have an independent error model, for instance, where for each qubit independently has a probability p of having an error. And if that's the case, then if you have n qubits, then the probability of having having an error on one of those n qubits is roughly n times p. And that's the part that's kind of intuitive and standard because it's basically classical. But in a quantum system, you can also have errors that accumulate at a kind of faster rate. So for instance, suppose you have a qubit that's rotated by an angle theta, right? And so if you measure, after you do one of those rotations and you measure the qubit to see if it's the original state or a different state, well, the probability of seeing the error is about theta squared. So let's call that p. That's the probability of seeing an error. But now suppose you rotate it by the same angle theta n times, and in the same direction. Well, now it's rotated by an angle n times theta. And when n times theta is relatively small, the probability of seeing the error there is about n squared theta squared, or n squared times p. So the errors have built up as the square of n rather than linearly with n. And this type of error can certainly occur in quantum systems. A very common cause of that is miscalibration. Like, for instance, you have a slightly wrong energy level, and so you do a rotation, but it's not quite the right rotation. It's off by some small angle. Or you do something for a little too long or a little too short, something like that. So, coherent errors definitely occur in quantum computers and real quantum systems. And this fact that they can build up quadratically can be a bit of an issue. So why is it an issue? Well, because we can't expect the error rates to be incredibly small, we expect that to build large quantum computers, we're going to need to encode them using quantum error correcting codes and fault-tolerant quantum computation. And then there's this theorem called the Threshold Theorem, which says that, yes, we can do that, for a wide range of noise models, there's a threshold error rate. And if the error is below that threshold error rate, then the fault tolerance will work, and we can have logical qubits, encoded qubits, that are as correct as we like them, as have error rates as low as we want. And so, of course, it's very important to know what that threshold error rate is, because that sets the target for experimentalists. Experimentalists have to get their noise below that threshold error rate in order to be successful in building big quantum computers. And we can prove that, at least for some theoretical models, that it's at least 10⁻³ for simple depolarizing noise. simulations suggest it's actually better than that, more like 10 to the minus 2, probably a little bit higher. But the very, very best codes that have the very best thresholds, they're incredibly inefficient, not something that somebody would ever use, as far as we know. We don't know better codes, but there are some quite good codes called surface codes, which are sort of the leading candidates for practical fault tolerance right now. They have a threshold that's almost 10 to the minus 2. So if you can get your error rates down below that, then you can build a big quantum computer. But I should say that, again, this 10 to the minus 2 is specifically for depolarizing noise, which is a very simple and symmetric type of noise, where with probability P, you have an error. And then when you have an error, it could be anything. It could be X, Y, Z, any poly, which is equivalent to having some probability of just randomizing the qubit and some probability of this qubit being left alone. So that's an example of a stochastic error. You remember that stochastic errors build up linearly. Now, coherent errors, suppose you have a coherent error in the system, well, that'll build up quadratically. And why is that important in this threshold calculation? Well, the thing is that the way you do this calculation is you say, well, there's many different places we can have errors, or really pairs of errors, because that's the sort of thing, or groups of errors. That's the sort of thing that ruins fault tolerance. You have many errors at once. And there's many different ways that can happen. And if those, and each of them has some rate that it can happen, right? Some probability P of happening. And so if there's n of those and there's stochastic errors, then the probability of getting any of those is about n times P. And by saying, well, n times P should be less than the error rate, the unencoded error rate, that roughly speaking gives you the threshold. But if they're coherent errors, then you shouldn't be calculating n times P, you should be calculating n squared times P. And that means that the error rate that you can get out of the proofs is much smaller, that the probability that you should accept is more like 10 to the minus 6 rather than 10 to the minus 3. Now, this is kind of the worst case, right? This is assuming that all the possible different errors will add up coherently. And that's not going to happen in practice. Indeed, it can't really happen because the errors just work in ways that can't possibly add coherently. But it's certainly possible that some of them could add coherently and could make the error accumulate faster than you're expecting if you're just looking at the and so this is kind of an open question as to how much difference it really does make. There's some simulations that suggest it's not too much worse, so it's still maybe order of 10 to the minus 2, 10 to the minus 3, but you might lose a factor of 2 or a factor of 3, which is already enough to hurt you in terms of the actual performance of your fault tolerant system. So you'd like to get a good sense of how the coherent errors work. Now, yeah.
Then sorry, question here. So is it only a matter of numbers? Do we at all have threshold theorems for any coherent error as well?
Yeah, so the threshold theorem, there is a proof for kind of independent coherent errors. So where the errors are a tensor product of what happens on different qubits, or for errors where the correlations between different qubits decrease according to some exponential. So there can be correlations, just not very strong long range. Not long range is okay, but large scale correlations. And there's also even proofs that work for non-Markovian error models, for a variety of non-Markovian error models. So we do know that there exists a threshold for a wide variety of models, including many coherent error models. There's still some holes there, but coherence in principle is not a problem. It's just the question of what the actual threshold is.
Thank you.
And so I don't have a slide on this, but I guess I also want to comment that another reason to know about coherent errors is that there's other ways to deal with coherent errors. Because they're always the same, there's not some probability going on there, you can get them to cancel out. And that, so for instance, if you have an over rotation one time, then maybe the next time you do an under rotation. Or you can do something, you can flip it and get the over rotation in the opposite direction. And so long as they're kind of consistent over rotations in the same amount, in the same direction, you can get them to cancel out much better than you can get stochastic errors to cancel out. So actually, in some ways, coherent errors are worse, but if you know about them, you can sometimes make them better than stochastic errors. So that's another reason that you'd be interested in knowing how much coherent error you have in your system. Okay, so so then the question is, how do we figure out whether our error is stochastic or coherent, and how much coherent error we have? Well, so one standard way of measuring errors in a quantum computer is called randomized benchmarking. And so randomized benchmarking, you basically do kind of a random circuit, usually using Clifford group gates. And at the end of it, you measure whether you do it for different amounts of time, and you measure the kind of decay rate in the fidelity to the original state. And the thing is that because it's randomizing these things, it doesn't distinguish between coherent and stochastic errors. Basically, the randomization turns coherent errors into stochastic errors, and then it just adds them all together. So that's not a way to tell. And so, if you estimate your error rate using randomized benchmarking, and it's all stochastic errors, you might think, oh, everything is great. But if it's all coherent errors, you might think it's not so great. If you want to be conservative, then maybe you think, well, I have to assume it's coherent errors, and then worry about that. Okay. So other techniques you could use.
Can I ask a question about randomized benchmarking? So there is a version called purity randomized benchmarking, which detects the coherent errors. Yeah.
So I think that's there's a lot of different variations, and so I'm not 100% sure, but there's a quantity called unitarity, which you can use randomized benchmarking. And so that gives you some information about the coherent errors. It's not a direct measurement of the coherent error rate, and in particular, it doesn't tell you the coherent errors in individual gates. It just tells you kind of the coherent error rate averaged over your set of gates. So that in some cases that might be enough to tell you what you want to know, but in other cases it might be inadequate. And one thing in particular that randomized benchmarking, including unitarity, doesn't do is it doesn't tell you very much about state preparation and measurement errors. And that's kind of deliberate, and it's generally viewed as a positive aspect of randomized benchmarking because they want to focus on the errors in the gates. But actually, to make a fault-tolerant protocol work, you do need to worry about errors in the state preparations and in the measurements. And so those things can also have coherent errors. And randomized benchmarking by design kind of washes those out because it does a long set of gates and you have only a little bit of measurement contributing. So that's another thing that I'll address with this approach. Now, another approach you can use is process tomography. So process tomography will tell you everything, assuming it's a Markovian noise, will tell you everything about the error. And so that's great. Obviously, that's useful information. You can get a complete characterization of the error. The problem is, again, we have to worry about errors in the state preparations and in the measurements that we're doing. And so process tomography, in order to work when you have noisy everything, you have to use something called gate set tomography, which is kind of simultaneously measuring the errors in your state preparations and your complete gate set and in your measurements. And that's a very expensive procedure. So while you can do that, it's a lot of work and a lot of measurements that you have to make in order to get that information. And so if you're interested in only kind of part of that information, it makes more sense to do a more direct measurement of the thing that you're interested in.
Can you explain why measurement preparation errors are important for fault tolerance? I mean, you'd maybe naively think that a single, they occur only once, and therefore somehow they wouldn't.
Right. Okay, so usually the way fault tolerance is done is you encode your state using an error correcting code. Well, okay, there's two things. So first of all, even in an unencoded computation, yes, it's true that maybe you only measure at the end of the computation, and there's only one of those, but that one can still wreck your computation, right? I mean, if maybe you're willing to accept an error rate of 10 to the minus 2 or 10 to the minus 3, but suppose you don't want to accept that. Suppose you want a much better answer. Then you need some sort of error correction to achieve that, and the error rate in the end matters. But more important for fault tolerance is the fact that the way it's normally done is you encode using error correcting code, and you don't wait until the end to measure whether there's errors or not. And you shouldn't wait until the end because the errors are accumulating throughout your computation. So if you do a very long computation, you have to periodically flush those errors out. And the way that's normally done is by measuring what's called the error syndrome, kind of at regular intervals. And every time you do that, the easiest way to do that is to make an actual measurement, get some classical information, and feed that into a classical computer to figure out what the error is, and then adapt to it. And if those measurements that you're doing have errors in them, which of course they will, then that can cause your fault tolerance to fail because you get the wrong information about what errors you have. So if the error rate is low, like comparable to the other gate errors that you have, that's okay, that's fine, that's included in the fault tolerant protocols. But if it's much higher, or if it's a different kind of error, like it's these coherent errors, where it's everything else as stochastic errors, you might worry that it can accumulate faster than you're expecting, and wreck your fault tolerance just due to errors on the measurements.
Yeah, there is another method of randomized measurements that calculates trace row square related to Renyi entropy.
Yeah. So I mean, I guess I don't know offhand what you're referring to, unless it's. I mean, what's the formula for unitary?
I think from Peter Zoller.
Okay. Anyway, yeah. I mean, there are other techniques to do this. I'm not aware of anything that that achieves the question that I'm answering, that I want to answer, other than measuring everything. And so in particular, here maybe I can move on here. So the scenario that I want to imagine is that we have a system. It possibly has coherent errors in it, and we want to figure out how much coherent error it has, or if it has coherent error, but we don't know anything about the type of error that might be there. But I am going to make a number of other assumptions about the system. So I'm going to assume that the errors are quantum operations, and so that when we have circuits, the noise is Markovian. Most of these other techniques will also assume that. This is something for the low error rate regime. Mostly I'm going to talk about qubit errors, and in particular noise channels map qubits to qubits. So I'm not talking about errors that leak into some other degree of freedom. And at the beginning, I'm just going to talk about the quantum channel case where we have a perfect quantum computer. We send it through a noisy quantum channel, and we have perfect quantum computer at the other end. But later on, we'll allow errors in the gates and state preparations and measurements. I'm not aware of another technique that kind of gives the same sort of answer, which is you don't know anything about the coherent error, but you always want to be able to detect it, no matter what the coherent error is. There's a lot of techniques that will work for like specific kinds of coherent errors, or will work sometimes with coherent errors that will work for like the unitarity, give you some sort of average information averaged over a bunch of different things. So this is a technique that under these assumptions will, in a gate or measurement, it doesn't actually work for state preparation, although I have a different protocol that does, will tell you in that particular kind of gate, provided every time you do that gate, you get the same coherent error, it will tell you how much coherent error you have, whether you have it or not, no matter what that coherent error is. Okay.
Sounds good.
Okay, so yeah, so okay, so that's the scenario that I want to consider. So now the next thing to do is to define actually what I mean by coherent error in a rigorous way, and that actually turns out to be surprisingly difficult. So the intuition that I described before is that the distinction I'm making between stochastic errors and coherent errors is that stochastic errors accumulate linearly and coherent errors accumulate quadratically. So, so specifically, I'm going to consider a situation where we're sending n qubits through the channel. We're going to send create some state, maybe an entangled state, send it through the channel, and then measure on the other side whether it was correct or not. When we send n qubits, does the error scale linearly as a function of n, or does it scale quadratically as a function of n? And the problem with just making that definition as the distinction is that if you go to large enough n, the error rate will always go to 1, right? And so you'll stop scaling as n squared and n. And obviously, for any given particular states that you might put in, there'll be some things that are not scaling, some sub-leading corrections. And so to really see the asymptotic behavior, you have to go to very large n. But at very large n, the error rate is 1, and you don't see any kind of scaling at all. So the solution that I came up with to this is to say, well, what I'm going to do is I'm not going to look at a single quantum channel, a single noisy channel. I'm going to look at families of channels. I'm going to look at families where the error rate goes to 0. Okay, and so suppose you have such a family of channels, so C sub r, and so I'm going to parameterize this family by the worst case infidelity. So so f and r. So if you look at f of, well, okay, so if you imagine putting pure states into the channel, then the state that you get out, you can look at its expectation value for the state psi that you put in, and that's if you minimize over all psi, that's the worst case infidelity. And then if you have an n qubit state psi, and you put it through the channel, each qubit through the channel, so that's n uses of the channel, then you'll get this formula here for FNR. And again, we're minimizing over psi, so that's the minimum possibly entangled state, minimum fidelity over all possible entangled states. And so R is equal to F1R, but then FNR, sorry, R is equal to 1 minus FNR, F1R. And then FNR, 1 minus FNR could potentially be worse. It could scale linearly with n, it could scale quadratically with n. But again, for large enough n, fidelity will always go to 0. So so what we're going to do is we're going to look at the leading order behavior as a function of R. And as R goes to 0, well, the fidelity goes to 1, and f of nr will go to 1 as well. And so we're going to look at the limit of 1 minus FNR over R, and that's going to be this function G of n. And then the question is, how does G of n? And G of n can actually asymptotically in the limit of large n scale linearly. And in that case, we say it has linear accumulation, and that's the stochastic error, or it can scale quadratically, and that's the coherent error case. And so it turns out, if you look at channels, that actually those are the only two possibilities, because we're looking at the worst case infidelity, that either it scales linearly or it scales quadratically.
Okay, and then I can explain again how R is defined. Is it defined independently of the definition of F and R?
Well, sort of. So R, yeah. So R, first of all, R is a parameter. So you have the channel C sub R. So each R gives you a different channel, which normally you think of as just scaling some error parameter. And then, but the parameterization is kind of arbitrary, right? You could reparameterize and you'll have the same family of channels. And so I'm picking the parameterization such that R is equal to 1 minus F1R. So R is the worst case infidelity for single use of the channel.
Single on a single qubit. Yeah.
Yeah.
Okay. Mm-hmm.
Okay.
Mm-hmm.
So anyway, so this is what I'm going to use as my definition of what a coherent error is. And so it turns out when you start to analyze this, that if you write the channel in its Krauss form, and you choose the Krauss form correctly, that this property of whether you get linear accumulation or quadratic accumulation only depends on a single Krauss operator. So how does that work? Well, again, remember we're working in the case where R is fairly small, the fidelity is quite high, the errors are low, and so it turns out in that case you can write the Krauss operators with one big Krauss operator, and the other Krauss operators are small. And small means in this case about R square root of R. So so if you look at the Krauss operators of CR tensor n, so n copies of the channel, well, that will also have one big Krauss operator, which is A0 tensor n. And then I'll have a bunch of Krauss operators that are about size square root of n, and those will have n minus 1 A0s and one AK where k is not 0. And it'll be 10, again, tensor products of those. And there's n of those, okay? And moreover, because it's the sum of these things, there's the density matrix is the sum of those things, and so they add incoherently. You cannot get interference or anything like that between these different terms. So all of those Krauss operators with one non-zero A0, one AK that's non-zero, are adding incoherently, and there's n of them, so they can only ever create an error that's linear in n. Because the terms that have two AKs on different qubits are smaller by R, well, they are sub-leading order. So the leading order behavior is going to be dominated by things that are either order n or that are this A0 tensor n Krauss operator. So that's all we have to look at to determine if it's coherent or stochastic channel. We only have to look at A0 tensor n. So then we're going to write A0 using basically the singular value decomposition as U times D. In some choice of basis, D can be diagonal. In another basis, it'll be Hermitian. And then U is unitary. And it turns out that D never produces quadratic accumulation. It just produces linear accumulation of errors. But U can produce quadratic accumulation. And so that is the answer as to whether the channel has coherent errors or not. You look at the leading Krauss operator, A0, and you write it in this form U times D. And if U is the identity, then it does not have coherent errors. And if U is not the identity, up to the order that you're working, then you do have coherent errors. And that's just like the answer to the question. Now, obviously, in an experiment, you don't know what A0 is, you don't know U times D, but theoretically speaking, this is the answer to the question. Okay, are there any questions on that?
So you're saying that if D is, as long as D is not identity, you'll get linear accumulation of errors, basically.
No, it's the other way around. If U and D, so first of all, identity means here like order R type contributions. Obviously, things can be much smaller, and then you kind of don't see that. But if you can have both U and D, so if U is the identity and D is not the identity, then you'll have linear accumulation. If U is if U is not identity and D is the identity, then clearly you'll have quadratic accumulation. But if both U and D are, provided they're about the same size, then you still can have quadratic accumulation.
Okay.
So what will happen is you'll have a linear term, and you always have linear terms actually. You have basically a linear term from D, but then for large enough n, it will be overwhelmed by the quadratic term from U.
U has to be R close identity?
Yes, in a way that I'll make a little more clear on the next slide, I think.
Mhm.
So it's the yeah. Why don't I go to the next slide? So what's going to happen is we're going to write U. I mean, it's a rotation basically about some axis because we're talking about qubits, and so we have some vector v in the block sphere that tells us what the rotation axis is. And then we have an angle theta that says how much we rotate by. And what it is that theta squared, which is kind of the probability of having an error if you just have U, that should be order R. Because that's the thing that's kind of comparable to the error probability.
Daniel, does your framework also can explain coherent how to analyze coherent errors when the channel works on 2 qubits at once, or is it just?
Yeah, so in the paper I talk about this, and it's actually important to say for the C0 gate. Yeah, basically you can do the same thing for qubits, or a 4-dimensional state is 2 qubits, and this whole argument works the same way basically. So
it might be not commuting. I mean, one in some sense.
Sorry.
It could be that you have a 2-qubit unitary error, and then it will not commute with the other 2 local unitary error, or so.
Oh, I see what you mean. Yeah. Right. Okay. Right. So that is a little different from qubits. So yeah. So when I say it works the same way, that's only when you have like these 2 qubits over here, and you have an error that acts on them, and these 2 qubits here have a separate error. When you have overlapping things, yeah, I don't know what to do. Mm-hmm. So that was one of the assumptions. I didn't make a big deal about it, but yeah, I'm assuming that the errors, if you have a 2-qubit gate, you can have errors acting on those 2 qubits, but otherwise the errors are separate on the different qubits.
Are you also assuming that the error acts in the same way on each of the qubits?
Yes, I am assuming that at the moment. So if there's a little bit of difference between the errors, if they're kind of very similar but not identical, then basically the same thing holds. There's yeah, basically works the same. If it's very different, then that's no longer true. Let me get back to that later. So there are some other things you can do, and one of the techniques that I'll mention later kind of addresses this.
So Daniel, in this GG example,
yeah.
So I should conclude from the n-squared term that there are coherence errors.
That's right. So yeah. So now let's move on to well, okay. Before I do that, let's talk theoretically about, again, are there any more questions about kind of theoretically speaking, can a channel see quadratic accumulation or linear accumulation?
So in this GG example, should I conclude that I have both incoherent and coherent errors, or because I have also linear accumulation? I have both, right?
Yeah. Okay. So then maybe let's go through this. So yeah. So there actually are usually linear terms as well as quadratic terms. Mm-hmm. But again, remember, we're thinking about the large n limit. And in the large n limit, the quadratic term will always win out.
Oh, then okay, I see.
So that's kind of, remember that this definition is done under 2 limits, right? We're taking the limit as r goes to 0, and then we're taking the limit as n goes to infinity. Okay, so yeah, so the kind of the standard example of getting this quadratic accumulation of error in the scenario that I'm talking about, where you have n qubits going through a channel, is this GHZ state. So if you take 0, 0, 0, 0 plus 1, 1, 1, 1, 1, and each qubit gets a small rotation in the z basis. So 0 goes to 0, 1 goes to e to the I theta 1. Then we get this state 0, 0, 0 plus e to the I n theta 1, 1, 1, 1. And if you look at this, well, that's the original state plus some order theta, order I should say order n theta amplitude of 0, 0, 0 minus 1, 1, 1, 1, 1. And so if you were to measure in a basis, including the GHZ state, you'd find a probability of order n squared theta squared of seeing the error. So that's exactly your quadratic accumulation. And it turns out that for that particular error, the Z basis rotation, the GHZ state is actually the state that sees the biggest quadratic accumulation. It has the largest constant factor in front of the quadratic. But what happens if we have not the Z basis rotation, but some different unitary? Well, so we expand it this way, as I said, cos theta identity plus I sine theta V dot sigma. So this is, again, picking the axis of the block sphere and the rotation angle. And so in particular, we're expanding it in terms of qualities. And it turns out, you can just do the calculation, it's very straightforward, that when you do this, well, you will get some linear term in n, but you'll also get a quadratic term in n. And that quadratic term will be n squared theta squared times vz squared. So the z component of the axis gives you the quadratic term. So if you have, the z basis rotation, vz is 1, and this is a big term. But if you have an x or y basis rotation, or in the xy plane, vz is 0, and you won't see any quadratic accumulation at all for that particular state. But if you see something that's around some other axis, then you look at the projection on the z basis. If we knew that we had something that had a significant z component, we could say, well, we can detect the coherent error by just sticking a GHZ state through the channel for different values of n and seeing how the error accumulates as a function of n. But what if we have something that we don't know what the coherent error is? It could be about any axis. It might not have the big Z component. Well, we can just pick a different GHZ state. We can pick a GHZ state in the x basis, and that will pick up the x component of the axis, or the y basis, and that will pick up the y component. And because x, y, z components are all the components there are of that axis for qubits, that by doing those three bases, the x basis, y basis, and z basis GHZ states, we can always detect every coherent error. And moreover, because the actual amount, the actual coefficient of this n squared term tells us vz for the z basis, vx or vy, then by making those three measurements, we can even figure out exactly what the coherent error is, what the v is and what theta is. Now, again, you can do this for qubits, and then instead of x, y, z, you have to use a mutually unbiased set of bases. And unfortunately, it doesn't work as well there. There you always detect if there's a coherent error, but you don't immediately get enough information to tell you exactly what the coherent error is. But anyway, going back to qubits, we get this protocol, again, for the channel situation. We create GHZ states in the x, y, z basis, send them through n copy, each sends through n copies of the channel for different values of n. And then we have to measure to see if there's an error. And so instead of measuring the entangled basis, it's a little bit easier. You can just measure, if you have the z basis GHZ, you can measure in the x basis. And if you get an even parity state, that's no error. If you get an odd parity state, that's an error. And that's because the 0, 0, 0 plus 1, 1, 1 state, if you do the Hadamard measure in the x basis, that gives you a superposition of all even parity bit strings, whereas the minus GHZ state gives you a superposition of all odd parity bit strings. So, and then if you have the x or y basis GHZs, you can measure in the z basis, and again, get that same information. And so that tells you, by the number of times you get the odd parity outcome, that tells you the error rate for n, for each of these three cases, x, y, and z. And then you see how that scales with n. And if it's quadratic, then you have a coherent error. If it's quadratic for any of those, x, y, or z, you have a coherent error. And if it's linear for all three, then you have only stochastic errors. Okay, does that make sense?
Yeah, I mean, I mean, kind of, you're assuming that you can prepare a GZ state, but I mean, are you going to discuss?
Yeah, that's right. So again, this is based on the first scenario where we're only trying to find noise in the channel, and we're assuming we have a perfect quantum computer at the start and a perfect quantum computer. Alice has a perfect quantum computer, Bob has a perfect quantum computer.
Yeah.
The only errors are the errors in the channel. So the next step is to say, well, that's not true. We have errors making the state, and how do we deal with that? But I want to make sure people understand this protocol first. Okay, I'll take that as a yes. Okay, so what do we do when there are errors in the gates, which is the realistic situation? Well, what do we have to worry about? Well, first of all, we have to worry that making the GHZ state will already have some order n squared accumulation of errors. Now, if the errors in our gates that we're using to build the GHZ state are stochastic, well, we don't actually have to worry about this because making a GHZ state can be done using O of n gates. So if there's stochastic errors, those errors will accumulate there'll only be a linear term in n in the infidelity, and we won't confuse that with the n squared that we see from a coherent error in the channel. So that's good. But the problem is that if the gates that we're using also have coherent errors, then they can accumulate quadratically, and we won't be able to distinguish between coherent errors in the gates that we're using to make the GHZ states and the coherent errors in the channel that we're really interested in. And so my solution, yeah.
Is it still clear that if you have errors, the GHZ state, preparing a kind of a GHZ state with errors is the optimal state? I mean, it could be that there's some state that you
sorry. So if you don't have errors in your gates, the GHZ state in the correct basis is the optimal state. Obviously, we don't know the correct basis, so that's why we use these three different bases. If you do have errors, yeah, I don't know. I mean, then it's a more complicated thing. It depends on what the errors are and what the kind of the detailed assortment. I mean, obviously you have some gates that are low errors and some gates that are high errors that might suggest one kind of state.
Yeah.
But roughly speaking, it's kind of only GHZ-like states that really produce this quadratic effect. Yeah. So I don't think you're going to get a big difference by studying different states, but it's not something I've really looked at closely. Anyway, so what I'm worried about now is that is how to distinguish between the coherent errors in the gates I'm using to make the GHZ state with the coherent errors that I really want to study. And the solution that I'm proposing is to use randomized compiling. So that's a technique that can turn gate errors into can turn coherent errors into stochastic errors. So remember I said for randomized benchmarking, doing kind of these random gate sequences kind of cause the coherent errors to average out and turn into stochastic errors. So that's basically what I want to do here. And to do that, I'm going to need another assumption, which is that we have polys, X, Y, and Z, that are very low noise. And in some systems, that's a good assumption. In some systems, that's not a good assumption, but I'm going to assume that. And so the way this works
just
is that—
Daniel, if randomized compiling is really so effective in turning coherent errors into non-coherent errors, then why are we worried about coherent errors?
Yeah, so that's a very fair question. And so there's two reasons. And so one of them is that there's potentially a little bit of overhead in randomized compiling. So if you don't have coherent errors, you probably wouldn't want to bother to do it. I mean, in some cases, there won't be overhead because you can kind of combine the extra gates into the gates that you're already doing. But in other cases, there will be a little bit of overhead. And the other reason, there's really three reasons. So another reason is, as I said, that if you have coherent errors, sometimes you can get them to cancel out at a higher rate than you could for stochastic errors. So in some cases, it's actually better to have coherent errors. And so that's a reason that you want to know that you have coherent errors so you can do that. And then the third reason is kind of a diagnostic, in that if you're an experimentalist, you have a gate, it has some noise level. You'd like to kind of know what's going on with that so you can improve it and get it better. And obviously, what I'm talking about is only giving you limited information about that. But finding out that it's a particular type of coherent error or a coherent error that does a specific thing can be useful diagnostic information that lets you say, oh, well, I need to improve my timing or stability of the energy or something like that. Okay, so how does randomized compiling work? So the idea is that if we do, so if you have a channel and you do a random poly before and then the same poly after, well, if the channel is identity, the polys will cancel out, nothing will happen. And if there's some noise in there, by averaging over the polys, what happens is you turn the noise in this channel into a stochastic noise channel, one that's a mixture of polys. And so when you do this in a gate, well, they're not going to cancel if they're the same, but they'll cancel if it's a Clifford group gate, then they'll cancel if these two polys are related by conjugation by the gate. So it turns out, for instance, that if you do X Hadamard Z, then that's the same in the absence of noise as just doing the Hadamard, because Hadamard transforms X into Z and vice versa. So, so if we do a random poly before the gate and then the corresponding one transformed by the channel after the gate, then when there's no noise, they cancel out. But by averaging over these polys, we again turn the stochastic, the coherent error into a stochastic error. Now, obviously, in any individual case, we're only doing one of these. We're not averaging. But in order to see any kind of statistics, we're doing many runs of this circuit of these channels, and so then when we add up over that, we're doing different ones in different times, and then basically effectively we are averaging over the different polys. Okay, so so if we do this for the Hadamard gate, then basically we're turning the noise in the Hadamard gate into stochastic noise. And then we can do it for the other gates too. Do it for the C0 gates. And again, you have to propagate the errors through the polys through the C0 gate to find out what to do on the other side. We can even do it for the state preparations. There we don't need to do bit flips, because that would change a 0 into a 1. That's not what we want. But we do Z's, which so the point is there can't be, sorry, let me rephrase it. So there can't be a coherent X error for the state preparation, because 0 plus 1 is if you kind of analyze the way it works on the state, will not cause a quadratic buildup. Well, sorry, that's not right. Anyway, this is maybe the right way to say it. So if you do random Z, half the time you do the identity, half the time you do Z, and you have a state that's like alpha 0 plus beta 1, then that Z randomization converts it to a mixture of alpha squared 0 0 plus beta squared 1 1. And so that's an incoherent mixture. And so obviously there's not going to be any interference between those two cases. Doing that for the X's doesn't help any, because that will just mix up the 0 and the 1, and it won't eliminate any interference. So in any case, for state preparations, we only need to do randomized over I and Z, and similarly for measurements at the end. And then the next thing we can do is, well, we're doing it for adjacent gates here. So we have a Z and a Y, and so we can combine those into one poly. That's just a slight space saving thing. And then we can do it for the whole encoding circuit like this. And we can do it for the measurements at the end. We're measuring the X basis here, so I put in some Hadamards and some measurements, and we do them around those. And so now, but the one thing that we don't do it for is the channel. So we want, in the absence of noise, we want all the polys to cancel out before the channel. And so that we're back to the correct GXZ state that we were trying to make. And so if you work it out for this particular example, that's true. So like this Z here at the end, well, it looks like it's causing a Z error here, but because this state was a 0, it's not actually. So if you apply all of these polys here, you'll still have the correct GXZ state. We put it through the channel, and then again we do some polys, and the upshot is that because we're not poly twirling for the channel, this thing can still see its coherent error, whereas everything else can only see stochastic error. And so that means if we see quadratic accumulation, it must come from the channel. So we can upgrade this to measure the errors in gates rather than channels. And the way we do that is we use the randomized compiling to make a GXZ state. And then suppose we wanted to measure the error in a Hadamard gate. Well, then what we're going to do is we're going to do the inverse of the Hadamard, which is again the Hadamard, and we're going to twirl that stochastically. And so now we have a GXZ state with Hadamard applied everywhere. And then when we apply the Hadamard gate, well, we're going to imagine that as an ideal Hadamard followed by a noisy channel. And so the ideal Hadamard first undoes this noisy Hadamard that we did. And so the effect is that we're doing this noisy channel on a GXZ state. And it's moreover, it's a GXZ state that's been prepared just using stochastic errors. So if we see a coherent accumulation of errors, it comes from the channel, which means that it came from the noisy Hadamards. Okay, so this works for a variety of gates, in particular for Clifford group gates. For C0 gates, it's a little more complicated because to do this, each line needs to be a 4-dimensional qubit. And so you can do the C0 between the 2 qubits in that 4-dimensional qubit. And there you need to use this MUB protocol rather than the qubit protocol. Okay, and then how do we test measurements using this technique? So that's a little bit different. And so how do we analyze the measurement? Well, the measurement, we can treat it, because it's a qubit that we're measuring, we can treat it as a 2-outcome POVM. So we have 2 outcomes, M0 and M1. And those are positive operators, so we can diagonalize them. So we diagonalize M0 into U, D, U dagger. And because M0 plus M1 is equal to the identity, that means that the same U also diagonalizes M1. And so then D here is like a bit flip error on the measurement outcome. Some probability of having a bit flip error on the measurement outcome. And then U is the coherent measurement error. And that's the thing we want to try to detect. So how do we do that? Well, if we could say, okay, we'll just use the same protocol. We'll make these 3 GXZ states, X, Y, Z basis, and we'll then measure on them directly. But if you do that, you see immediately you have a problem, which is that the 3 different GXZ states require measurements in different bases. And those different measurements might have different errors. Even if you do it by doing a gate first, well, that kind of changes the GXZ state to a different basis GXZ state. And so that's not giving you the information you need. But again, what rescues us is that not all types of coherent error are possible in a measurement. And so in particular, if you look at this U and you say, what if there's a Z basis rotation as part of the U, you'll see that it doesn't affect the measurement outcome, right? Because it's just changing the relative phase of 0 and 1, but then you measure 0 and 1 anyway. So it doesn't affect the probability of seeing 0 versus seeing 1. It's just the same as if that Z basis rotation was gone. And so that means that we don't need all 3 GXZ states. We only need the X and Y GXZ states. And for those, we can use the same measurement, the Z measurement. So that gives us our protocol for testing for coherent errors in measurements. We create X and Y GXZ states using randomized compiling, and we measure each qubit in the Z basis, count the parity. and then see if it's linear or quadratic as a function of n. And that again gives us x and y components, and that tells us u up to the z rotation, which again doesn't have any actual effect on the measurement. Okay, I'm running out. Yeah.
By coherent, what you say, coherent z rotations do not affect measurements. I mean, in the sense that you're thinking about the ideal measurement as just a measurement in the computational basis, and then you're saying as z measurement.
Yeah, that's right. That's right. Yeah.
Mm-hmm. Okay. Mm-hmm.
Okay. So yeah, so I'm running out of time. So let me just make a few comments. So there was this question of what if different qubits have different errors? And it's also a little inconvenient that you have to use n qubits to do this. But observe. So here's the circuit that I'm going to do. So it's not including the randomized compiling. So I'm making a GHZ state, which is a Hadamard and then some C naughts, and then I'm doing a channel on each qubit, and then I'm doing a measurement on each qubit, Hadamard or measurement, whatever. And you see that all of these qubits interact with the first qubit, but they don't interact with each other, right? And everything that happens on the second qubit is independent of what's happening on the others. So what I can do is I can rearrange this circuit. I can interact the first qubit with the second qubit, and then just go ahead and I can even measure the second qubit right away. And then once that's done, I could interact the first qubit with the third qubit, and the first qubit with the fourth qubit. And those can all be sequential. And in particular, I could just, take the second qubit, do it, measure it, and then reset it and use it as the third qubit, right? If I have that capability, obviously. And so really, I only need 2 qubits to run this protocol. I have this one persistent qubit that stays around, and then a second qubit that interacts with it and keeps getting a C naught and then a measurement and reset. And so that's helpful if you're worried about this issue of different errors on different qubits, because when you're doing this, the error that you're seeing is going to be dominated by the error on the second qubit. You use that second qubit n-1 times. It experiences n-1 times the error rate. And so any coherent error you see will be the coherent error on that qubit.
You can't do that for the testing the measurements though, right?
No, that also works for testing the measurements, right? Because again, it's the measurement of the
keeps
second
feeding
qubit.
back on the first qubits.
Well, you keep seeing the same. So this channel now is part of the measurement, right? So every time you do this measurement and you're doing it n-1 times, you're getting a little bit of that coherent error. And so what happens is basically it causes it to build up a phase in this first qubit every time you do that. And so that's why you see it at the end.
Cool.
Okay. Okay. So yeah, because I'm out of time, I won't really go into this, but the scenario that I presented was you have n qubits going through a channel in parallel. But of course, you'd really like to know, I have some more general circuit. Can errors build up coherently in that more general circuit? It could be the same, the same error occurring on the same qubit. It could be on multiple qubits. And there's other kinds of gates in between as well. How does that affect it? It turns out that this distinction between stochastic error and coherent errors has the same characterization in this case, that it's still just the leading Krauss operator, whether it has a unitary part to it or not. Maybe I'll skip this part in the interest of time, but basically there's other protocols that are kind of inspired by this more general technique. So okay, to summarize, the 3 GHZ states, X, Y, and Z basis, form what I call a maximally sensitive set of states, because they will always allow you to detect coherent errors with this quadratic buildup. So they're kind of maximally sensitive to errors because that's the fastest errors can build up in any kind of quantum system. And this kind of collection of techniques lets us measure coherent errors and the amount of coherent error that we have not just in channels, but also in gates. And by using randomized compiling, provided the poly gates are very low noise, we can kind of distinguish between coherent errors in the specific gates we want to test from the coherent errors in the rest of the system. Now, of course, any real system is going to have lots of different sorts of errors. And if there's and in a real system, you can't take this limit of R going to 0, right? You can't say, oh, I'm going to make my gates arbitrarily good and see what happens. You'll just have some fixed error rate. So what we're going to see is the things that are kind of first order in R versus second order in R. So if R is too big, then we'll get confused by these supposedly lower order effects. And if there's one source of error that's kind of much bigger than the other source of errors, and that source of error is stochastic, then we're going to see that we won't be able to see the much smaller coherent errors. Except because the coherent errors build up quadratically with n and stochastic errors build up linearly, even if the coherent errors are somewhat smaller, they're smaller by a factor of about n, then we might still be able to see them. So that's another kind of interesting factor here, is that the coherent errors, we can detect them when they're much smaller than stochastic errors. Because instead of having, if the stochastic errors are, 10 to the minus 3, we have to do 10 to the 3 gates or experiments or something in order to see them. Whereas the coherent errors, if they're 10 to the minus 3, by causing them to accumulate quadratically, we could see them, is only square root of, about 30 or so, right? Square root of 10 to the 3rd. Okay, and then there's some open questions. So for Qubits, I have this MUB protocol. It tells us, it always says if there's a coherent error, but it doesn't give enough information to fully reconstruct the coherent error. There are some things you can do to get the full information about the coherent error, but it would be interesting to kind of optimize that and figure out the smallest set of things that you need to do. The measurement protocol that I gave you only works for 2 outcome POVM, so it only works for measurements of qubits. So again, I'm not quite sure what to do if you have a qubit and you want to measure coherent errors in the measurement set. Okay, so that's it. Thanks.
Thanks, Daniel. So yeah, let's see if there are questions. I can start with a question. So if I look, I mean, you discussed the fact that when I prepare the states, when I use this randomized compiling, I'm going to have n and end up with an error that kind of accumulates only linearly on the GG state, in the preparation stage, right?
You mean because of the randomized compiling, right? Yeah.
But somehow, didn't you assume that somehow if I took into account that idle gates, just kind of waiting times, right? Actually also incur errors on the qubit, right? Suppose somehow then I would end up, actually I have n squared positions to insert an error in the preparation state.
Right, okay, I see. Well, not necessarily. So it depends on in detail how you do it. So okay. So maybe let's look at this circuit here. So so the way I've drawn it,
should we be looking at something? Because,
oh, sorry, I stopped the, sorry, that was a mistake. Yeah, let me think here. So yeah, okay, maybe it's actually better to use this version.
Mm-hmm.
So yes, I mean, obviously it's possible to design your GHZ circuit in such a way that there's n squared, kind of order n squared idle locations where the qubits are sitting around. But it's also possible to design your circuit in such a way that there's not. And so, for instance, if you look at this version of the circuit, where this qubit has to stick around for a time that's order n, because it's interacting with n other qubits.
The top one. You don't see what you're pointing at, but
oh, sorry. So the first qubit has to stick around for a time that's order n. But the second qubit, it doesn't. It's just a constant time, right? You make it, you get a C naught, you measure it, and then it's gone. And similarly for the third, fourth, et cetera, qubits. And so each of those is just around for a constant amount of time. And so, so there's only kind of a linear number of locations in the circuit. You create the qubit right before you need it, you interact, you measure, and then it's gone.
okay.
Now, obviously, this depends a little bit on your physical capabilities. But I guess the other thing that I should say is that that actually, if your idle is very noisy, like comparably noisy to your gates, then, well, no, well, that's not fair, because C naught could take longer. Yeah, I mean, right. Again, it depends on the assumptions. I mean, again, we're assuming kind of ideal polys. So at least some things that we can do are supposed to have low, kind of negligible error rates. But there probably are circumstances where the C naught gate takes longer, and so you have to worry about the waiting time for that, whereas the polys are short. That could be good.
But I mean, the randomized compiling does take care of. And you could kind of eliminate coherent errors in the C naught using the randomized.
That's right. That's right. No, I'm worried about. I'm thinking about what you were saying about having n squared waiting time. So if you don't compress the circuit in this way to n to order n locations, then you have to worry about quadratic amount of stochastic errors as well.
Well, basically, your protocol allows to amplify errors given even like just one pair of qubits, but I guess the amount of amplification would be limited in the practical setting by the time of the C naught and the reset, or is that correct?
Sorry, I mean the amount. So the coherent errors are effectively amplified by a factor of n relative to the stochastic errors. And you're limited the largest n that you can really do. Obviously, you're limited by how many qubits you have in your system, but also all of this only works in the regime where kind of n squared theta squared is still smaller than 1, significantly smaller than 1. And so that kind of limits the maximum n you can go to. Obviously, in the idealized case, you say, oh, I'll just take the channel to 0, and then eventually I can do very large n. But in real systems, when you can't do that, then that kind of sets the maximum size you can do. And so you need.
I guess once n equals 1 over theta, then you know theta, and then you're happy.
Yeah, but the point is that you need if your coherent errors are like a little bit smaller than the stochastic errors, that kind of limits the amount of amplification you can do for them relative to each other. So, if you have stochastic errors that are 10 to the minus 2 and coherent errors that are 10 to the minus 3, then you're probably okay. But if you have stochastic errors that are 10 to the minus 2 and coherent errors that are 10 to the minus 5, then you just can't amplify them enough before the stochastic errors just wreck everything. That's what I mean.
Okay. Other questions? Okay, so you said, I mean, Daniel, I'm not sure, I mean, maybe I didn't pay enough attention, but you said something about what happens when the errors in different qubits are actually not identical. There's some
right. So in the case where they're kind of very similar but not identical, what what happens is that you see that these error rates that you see, like the coefficient of the quadratic term is some sort of roughly an average of the z components of the coherent error on the different qubits.
Mm-hmm.
If they're very different, then that doesn't work. So, you know, the extreme case is where for some qubits you're rotating in one direction, some qubits you're rotating in another direction. In that case, they'll kind of cancel out, and you'll just see the linear scale. But if you do what I'm doing here on this slide, where you're just using the same qubit over and over again, then you don't have to worry about that because it's dominated by the error just on that second qubit that you're reusing many times. Now, if it's a different error each time you do the gate, then that's actually not a coherent error at all. That's a stochastic error in general. I mean.
Mm-hmm. Right. Mm-hmm. Mm-hmm. I think. Yeah. I mean, is there some sort of okay, I'm just kind of speculating. Is there some sort of analogous way to extract non-Markovian errors somehow, in some sense?
Yeah, that's a very interesting question. I mean, so the thing is that there's non-Markovian errors cover an extremely broad class, right? There's so many things that can happen. And some of them will basically be, you know, stochastic type errors. And some of them will be coherent errors, and some of them will do other things. And you can come up with errors that are kind of arbitrarily bizarre and designed to foil whatever kind of protocol you want to do. Or you can have a non-Markovian error that, you know, doesn't do anything for many, many times, and then eventually it's like really big. Or it's only really big if you do this particular set of gates, right? You know, and it's nothing until you do the last gate. So in order to meaningfully say anything about non-Markovian errors, I think, including characterizing them, I think you have to make some additional assumptions about what kinds of non-Markovian errors you have. But I don't know of a kind of a sensible way to do that kind of captures things that can happen in real systems, but it's still tractable and reasonable to work with.
Okay. Any other questions? I think I've asked plenty. Okay, if not, Daniel, thanks a lot. It was,
Thank you, Daniel.
Yeah. Really,
Thank you very much. It was very illuminating.
very good. Thanks a lot. And yeah, I hope to see you soon in person.
Yeah, it'd be nice.
All right. So, yeah, and good luck with there then. Hope that goes.
Thanks.
All right. So, bye-bye.
Bye.